Okay, so welcome to our lecture about data collection, processing, and presentation. So in this topic, we'll be covering three different aspects of data from collection until we can present the data. So let's start with data collection. Okay, so for collection, we have two methods. It can either be primary data collection, which is data collected by the researcher themselves, or basically we can refer to this as first-hand information. So this is when the researcher goes out and collects information firsthand and collates that information, processes that information, and then ultimately presents that information. And then you have your secondary data collection, which is data collected through other resources. We can collect through articles, we can collect through published journals, we can collect through news sources, publicly available information, or even government institutions. But let's start with discussing our primary data collection. Starting with perhaps the most common form of data collection is your survey or your questionnaires. Now, this could be performed face to face or through online platforms like Google Sheets or Google Forms, or sometimes you can even perform surveys through SurveyMonkey or other specialized websites for surveys. Now, before the advent of technology, surveys and questionnaires did require a lot of manpower for dissemination and collection because you would have to print all of your forms, all of your questionnaires, distribute them, and then distribute. And then eventually you're going to have to collect. So it took a lot of manpower, and at the same time, it takes a lot of time for us to disseminate the survey, distribute, and collect our survey questionnaires. So that's one of the major challenges of having or conducting a survey. Now, the other one is, of course, aside from the huge manpower needs, you also need a lot of funds because for surveys and questionnaires, you would have to be printing a lot of pages. And imagine from our previous lesson from sampling, a statistically significant sample, or rather the minimum sample size that we're usually going to compute for is about 70, maybe even as much as 400. And so if you're going to print 400 pages, take note that would assume that you only have one page per person. So let's say you need at least, let's say, 5 pages for the survey, including the informed consent forms, the participation forms, and all the formal research agreements that you're going to have with your respondents. Then you would have at least 2,000 pages to print. And then you're going to have to disseminate these 2,000 pages to the 400 people that you're going to include in your research. And then you're going to have to collect your 2,000 pages from your respondents. And not only that, you're also going to have to tally all of their responses. So you're going to have to check individually if they answered all the questions. You're also going to have to check if all the questions are answered sincerely, because we cannot avoid manpower, or we cannot avoid respondents that would answer the survey questionnaires half-heartedly. So we have to make sure that our data or the collected surveys do meet the standard requirements for our data analytics. Okay, so there are definitely a lot of challenges, but thankfully, most of these challenges have been solved by our technology through online platforms like Google Forms, SurveyMonkey, and other specialized survey websites. Next, we have interviews. So, interviews require direct interaction with the respondents, which can be done in person through calls or through online video conferencing. Now, the advantage of interviews over surveys is that interviews allows us to collect verbatim data, meaning that we can collect our respondents' responses to our questions word for word. So we do have and we can quote our respondents. Now, typically, interviews are done for scoping studies. That means that when we do interview, we usually want to identify, or rather, we don't seek to define a greater phenomena, but rather we seek to identify different avenues for research. Okay, so instead of using surveys as a means for us to answer questions, we usually use, or rather, interviews. We usually use interviews to come up with further research questions. So this allows us to be more intimate with our respondents. It allows us to go deeper into the questions that we're asking, allows us follow-up questions, and it allows us to observe the reactions and the mannerisms of our respondents as they hear the questions that we have for them. So, one major advantage of your interview over your survey is the personal interaction with your respondent. However, like your surveys, interviews can take a lot of manpower because you're going to have to again interact with your respondent for mostly or at least 30 minutes at a time. So assuming that you're just one person or there's just two people working on the research, then that 30 minutes per day translates to about 16 respondents per day. Okay, so it would take a lot of time, but maybe perhaps less manpower, but it would take a lot of the time of your already existing manpower. Okay, so that would be for interviews. Next, we have observations. So observations merely observe the samples or the respondents in their natural habitat or how they react to natural phenomenon without intervening. So the key term here is that we're not supposed to be intervening. So there is no intervention that's going to happen for observations. We simply want to observe what they're doing and how they react. Okay. However, it is also important to consider the possibility of what we call observer bias and the observation effect, which may skew the data. So that means when we say observation effect is that when a person is observed, okay, sometimes they would change their attitudes, which I would say again is something that that could skew or that could ruin the data that you're trying to collect. Okay, so we also have observer bias, which means that our researchers, when we observe our respondents, um, there might be bias. Okay, specifically and most commonly, we call it the confirmation bias, meaning that since we believe and we want our research to be positive or to have a positive result, we tend to look for certain characteristics that confirm our hypothesis. Okay, so it's important to consider to take more observers, to take outside observers and assess the data. Okay, it's also, again, we have to make sure that we try to be as discreet as possible so that our observation effect is minimized. Okay, so that would be for observations. Finally, experimentation. So experimentations are simply observations with the added intervention. What we're doing here is simply doing or taking our independent variable and our dependent variable and then measuring the effect of our intervention. Okay, so let me just change this to make it clear. Intervention. Okay, so what we're trying to do is measure how our intervention affects our dependent variable. Okay, and typically our intervention would go between our independent variable and our dependent variable but sometimes our intervention can be the independent variable itself. Okay, so experimentations are typically done through designing protocols to control variables involved in the experimentation, meaning that when we do experimentation, we want all the surrounding variables to be controlled, accounted for, and so that the only thing that can affect the outcome is our intervention. Variables may include the weight, the height. Variables may also include the age of our subjects, and so on and so forth. So these are all factors that could potentially affect our dependent variable, but we want to keep it outside of our design, and we want to make sure that all of these are controlled so that when we do our experiment, when we administer our intervention, the effect on the dependent variable we're seeing is purely from the intervention itself. Okay, so that would be experimentation. Now, just to give a quick summary of our methods of data collection, you have your surveys and you have your interviews. And these are methods of data collection that typically take nominal and ordinal data, whereas your observation and your experimentation would take interval and ratio data. Okay, so um, that is the reason why when you conduct surveys or interviews, there is typically a high sample size requirement. When you do observations and experimentations on the other end, our samples are not as important to be high. Instead, we need samples that meet our test requirements. Because what we're measuring here are not subjective variables. What we're measuring here are objective measurable variables. And so we are afforded a higher statistical power, and thus we can use a lower sample size than we would if we were to collect subjective data like surveys or interviews. Okay, so that would be our primary data collection. Moving on to our sources of secondary data, you have your first, your published resources, your online databases or journals, your government and institutional records, publicly available data, and of course, past research studies. Now, it's a common misconception that we're not supposed to be taking information or rather related literature from what we call as gray media. So when we talk about gray media, what we're referring to are articles that are not peer reviewed, but they are of course responsibly sourced, meaning that for instance, you see an article, it may not be peer reviewed, but sometimes they would list their references at the bottom. And if the references would be taken from government or institutional records and publicly available data, meaning that they are verifiable, then it is perfectly all right and perfectly fine to take research or to take information from gray media. Okay, so just a note when we're trying to collect secondary data. So that would be it for our methods of data collection. There are a lot of other ways or a lot of other specialized methods of data collection, but for our purposes, we're going to focus on the following that we've discussed. Next, processing. So basically, what we do with processing is we first trim and examine the data, and then finally we do our descriptive statistics. So we're going to cover in this part of our lecture, first and foremost, how to trim your data, how to process your descriptives, and finally, how to present. Okay, so this would be most likely in the other part, but we're going to again trim data, um, establish our descriptives or descriptive statistics. And then finally, in the next part, we're going to learn about the different ways on how to present that data. Okay, so first, let's learn how to group data. So on your left, on group data, on your right is how we grouped the data. So as you can see, you have a total observation of 10, and the same with your ungroup. You have a total observation of 10. However, the difference is that your ungrouped data is listed individually, while your group data is listed through what we call classes. Okay? And for us to be able to compute or to rather establish the classes, we use the following formula as you see below. So, quick disclaimer, this is not the only formula that we can use for class width. Sometimes our sample size can be replaced with a random number, let's call it x, from 1 to 15, sometimes 1 to 20. So it depends on the reference that you're using. But most textbooks, and perhaps the most frequent formula that I've seen, is this formula right here. Okay, so basically, it's your range divided by the square root of your sample size. So let's try to compute for this. You have your maximum minus minimum. You have the maximum and highest would be 53. So this is your max. And then your minimum is 30. So simply replace our variables 53 minus 30 and then divide it by the square root of your sample size, which is basically 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, if we input that in our calculator, you get 7.27. And we round this off, we get 7. And so our class width should be 7. So 30 minus 37 or 37 minus 30 would give us 7. 45 minus 38 again would give us 7. 53 minus 46 would give us again 7. Okay. And then we simply need to do the next thing we need to do is to count the observations that fall within that class width. So in this case, we're going to count how many observations fall between 30 and 37. So you have 1, 2, 3, and 4. So we have 4. And then we count how many observations fall within 38 to 45. So that would be 38. 1 and 2. And then finally we look for the observations that fall within 46 to 53. So 1, 2, 3, and 4. So you get 4. Okay, so that's how again we compute for our class width. Next, we trim the data. So when we say we trim the data, we remove the data that is not supposedly included in our data analysis. So first step is to set the parameters for your data and then archive all collected data that does not fill or that does not fit the set parameters. And finally, include all data that meet your parameters, which we refer to then as valid data. So basically what we're trying to do here is to ensure that the data that we're going to proceed into data analytics would be valid and verified. Okay, so next we move on to our descriptive statistics. Now, for our descriptive statistics, we start with our measures of central tendency, specifically your mean, median, and mode. Now, when we do, or rather, our mean, median, and mode as the measures of central tendency, for it to be or to appear as a normal distribution curve, your mean, median, and mode should be approximately equal to each other, meaning that your mean at the center should be equal to your mode at the peak, and your median, which bisects your data, represented by the line between. Okay, so let's start with the different formulas and the different ways on how we can find our mean, median, and mode. Okay, so for the average, it's a very simple computation. You simply summate all the observations and then divide it by the number of our observations or our sample size. Okay, and again, our mean is found at the center of our x-axis, surrounded by the different standard deviations that which later on we'll be talking about. So here is an example problem, or rather four example problems for our mean or average. So we take our average by column, and we go simply add them all, and then divide them by the number of observations, which is 5, and then we get our mean at the bottom. Okay, so I'm sure that everyone who's watching this video has already explored or at least computed an average once in their life, and so we're not going to dive deeper into how the mean or average is computed, but instead let's talk about how the mean or the average is computed for group data. So this is the same example earlier. This is what we used for the computation of our class width, and you can see that you have age and then frequency. So to compute for our mean or average for group data, you get the summation of x sub I times f sub I, or basically the average of our observations or our group divided by the frequency, or rather multiplied by the frequency, and then divided by the total frequency. So x sub I would be the average of the class width, f sub I would be the frequency of that class width, and then class width, and then f sub I at the bottom is your total frequency. So in this case, we're going to compute for the x sub I first, and again, it's just simply the average. Simply take 30 plus 37 and then divide it by 2. 38 plus 45 divided by 2. 46 plus 53 and then divided by 2, and you get your x sub I. And then next is to multiply our frequency with our x sub I. So simply multiply, and then you get your xifi. Simply add all of these observations and you get 415. So substituting our formula, you get x bar is equal to 415 divided by the total number of observations, or the total frequency, simply is 4 plus 2 plus 4. That would give us 10. And so you divide it by 10. And finally, you have 41.5. And then we box our final answer. Okay, so that would be our mean or average for group data. Relatively simple, but a bit more complicated than our simple mean for ungrouped data. Now, what I want to highlight for our mean is that our mean is very sensitive to outliers. And when I say sensitive to outliers, it means that if you have a ungrouped data set, let's say 10, 14, 15, 16, and then let's say 20, you're going to get an average about right near 15. So your average would be most likely on this side. However, if you replace one of the values with a An outlier, by the way, is a relatively larger number compared to the whole group. So let's say you get an observation of 57, which again is an outlier. Your 57 is going to pull your mean towards it. It's going to shift your mean, and you're going to have then a mean that is about the second highest observation. Okay. So your mean would most likely look like something like this: 14, 15, 20, and then 57. Your mean is going to be found somewhere here. Okay. So instead of being at the center, which by its name, by its classification as the measures of central tendency, it should be at the center. It's not going to be because our 57 or our outlier is going to pull our mean. So how do we solve this? One way to solve this is for us to ensure that all our data is valid. So there might be a reason or an unknown reason why in a data set with 10, 14, 15, and 20, we got a 57. So it might be an outlier because we were not able to control the variables that were needed to be controlled. So in essence, we can simply remove this. But if we're not allowed to, or we can't remove it because we have verified it to be valid, then the best thing that you can do is increase the number of observations. Okay? Eventually, if you increase the number of observations, this might prove to be a non-coincidence, meaning you might find observations that are closer to 57, and so your spread is going to, again, equalize and form a normal distribution curve. So again, the two things we could do is to check whether the data is valid or not. If it's not valid, we can simply remove it. If it's valid, then we increase the number of observations so that we can stabilize our mean. Okay, so that would be all the information that I would like to communicate with the mean. Remember, it's very important that we consider the implications of having a mean that is stable, because in the future we're going to be talking about the different implications, or rather the different tests that uses or compares the means of two groups. Okay, so again, very important for us to have a stable mean, because this is what, or this is the value that we're going to be comparing across different tests. Okay, next we have the median. So the median bisects the data into two parts, and the most important part of computing for the median is, of course, finding or arranging our observations from smallest to highest or highest to smallest. So it really doesn't matter if you're going from lowest to highest or the other way around, as long as it's arranged in order. And when you do that, you simply take the center observations and you get the average. Now take note, this is for an even number of observations, meaning in this case you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 16, 17, 18, 19, 20 observations. And so the center is composed of two units, 26 and 27. And for us to get the median, we have to get the average of these two values. Okay. Now it's a lot simpler if you have an odd number of observations, like so. In this case, there was one number deleted, and so you have an even number of observations on your left and on your right, and you simply have to take the center observation, which in this case is 26. Okay, so one important thing that you have to, again, consider about the median is, compared to the mean, your median is very, very resistant to outliers. Meaning that if you change one value, let's say you change 41 over here, and you replace it with another number, a very high number in fact, maybe we can change it to 125, your median is still going to be 26. Even if you change that to the thousands, but that would be questionable already, um, you're also still going to have 26 as your median. So no matter your outlier, no matter the value of your outlier, it does not affect your median, unlike how it affects the mean. Okay. Now, other terms that were used or that are used for median could be your P50, can also be referred to as T5. So these are rankings, meaning it's percentile 50 or decile 5. Okay, so basically that's how the median is. Simply bisects the dataset into two parts. When we say bisect, we mean divide, and with it as the center. Next, we have mode. For mode, it can either be multimodal or it can be unimodal. Simply means that when you say a multimodal dataset, it has repeated observations, or the highest number of repeated observations are frequent, meaning that in this case you have 19, 21, 32, and these are all considered modes. Now, for a unimodal dataset, you only have one observation or one most repeated observation. In this case, that would be 21. Now, for a normally distributed dataset, we usually prefer to have a unimodal dataset. And that is because, if you remember, as we've illustrated earlier, in our bell-shaped curve, your mode is actually at the peak. And so, a characteristic of a bell-shaped curve is that it only has one peak. So if you have multiple modes, or if your dataset is multimodal, then you're going to have a dataset that is mostly flat. So you're going to have multiple peaks, which would result in a platykurtic curve. Okay, so we're going to talk more about that when we tackle skewness and kurtosis. But for now, know that when we are looking for a normal distribution, we prefer a unimodal dataset. Next, we have our measures of spread. So earlier we talked about the center. Now we're going to be talking about the spread of our data. It includes your range, your standard deviation, and your variance. So we're going to be talking about these individually. Now the easiest measure of spread is your range. Simply is the maximum minus minimum. So you take the highest number or the highest observation, which is 45, subtract it by your lowest observation, which is 12, and you get your range. So we get a range of 33. Now, your range is not typically something that we use in descriptive statistics. We give more importance to our variance and your standard deviation, but nevertheless, it gives us a good idea of how far your lowest and highest values are. Next, we have a more complicated computation, variance. We have our formula right here. Variance is represented by s squared. So this is a representation of what we call the sample variance, is equal to the summation of x minus mean. We sometimes refer to this as the difference squared divided by the population, in this case, minus 1. So population is again can be replaced with sample size or small letter n minus 1. Okay. Now, using the dataset shown here, let's try to compute for the variance. Now, first step is to get the mean, which is 27.7. So again, if we compute for the mean or the statistical average, all you have to do is add all the observations So summate, and then divide it by the number of observations, which we know from earlier is 20. So again, we get the mean, we get 27.7. Okay, and then next, we compute for the summation of our deviation or our difference. Again, what we do is we take our observation, so each individual observation, and then subtract the mean from it. And then we get our deviation. We square each one, and then we get the sum of our deviation. So the totality of your x minus mean squared, we get 1726.2. So we can simply input that to the formula, 1726.2 minus 20 minus, or divided by 20 minus 1, we get 90.85. So this would be our sample variance. Okay. It's a long process, but it's a relatively simple one. All you have to do is subtract the mean from each of your observation and then square the answer to that, summate all those values, and you get your summation of your deviation, and then simply divide it by n minus 1, which is simply your sample size minus 1. Okay. And when we have our sample variance, it's easy to compute for the standard deviation. Simply take the square root of your variance. In the earlier case, simply 90.85, or the square root of 90.85. So we take the square root of both sides and you get a standard deviation of 9.53. So the reason why we look for standard deviation and variance is so that we can see how controlled or how close to the center our observations are. Despite our bell-shaped curve being hugely determined by our measures of center, your mean, median, and mode, our standard deviation serves the purpose of telling us if our observations are in fact closer to each other. So this allows us to check or to give a presumption. A low standard deviation would indicate that our variables were controlled, and a high standard deviation could be suspicious that our variables were not controlled. Okay, in this case, 9.53 would be a relatively high standard deviation. Typically, we look for, um, depending on your measure, a lower standard deviation. Okay, so that would be for our measures of spread. We can now talk about, since we've finished our descriptive statistics, we can talk about presentation. So there are various graphical representations of data that we're going to be talking about today that might be helpful to a researcher or a budding researcher. First is your pie chart. So your pie chart is very useful for representing proportions of the population, and this is very useful if we want to present how much of our observations covers the entire population. So it is at a glance, it shows us that the majority or the biggest part of our respondents only had 4 hours of sleep. And about the same, the students who have 8 hours of sleep and 6 hours of sleep are almost equal to each other, and they comprise the other half of our um, population or our sample size. So basically, what we can infer from this pie chart is that half of our population has 4 hours of sleep, while the other half has 8 or 6 hours. So we know at a glance the distribution of our respondents. Next, we have our bar graph. So our bar graph is useful for visually comparing frequencies of categorical data. Now, unlike your pie chart, which considers the whole population as the whole, your bar graph does not necessarily have any inferences regarding the whole population. Instead, what it can show us is how high or how far the differences are from each other. So we can see here that, of course, as with the earlier pie chart, our or rather the group that has the most hours of sleep is 4. Okay, so pinakamadami is 4 hours of sleep, and then you have 6 hours, and then you have 8 hours of sleep, which would present with the lowest frequency. So it allows us a comparison of the frequencies of the different groups or the different sets of data that we collected. Next, we have our histogram. Now, histograms are a lot like your bar graph. In fact, it is a variation of our bar graph, but this time it is used for quantitative data. And typically, a histogram would be arranged from highest to lowest. It would typically be if we had more observations, then we're going to find that our histogram is arranged from highest to lowest frequency. Okay, but this is just basically a bar graph that is used for quantitative data. And finally, we have our line graph. So our line graphs are used to show trends over time. So if your study involves a longitudinal or a long-term study, longitudinal or a long-term study, then it's very useful to present your data in a line graph. It allows us to see if there is a trend that is going up or going down or going up and then stabilizing. Okay, so these graphs or these charts are very useful for us to show the different trends in time. And again, one very good example of a line graph that we could probably infer is that the cases of HIV worldwide is actually steadily increasing. And so, at a glance across different years from the 1960s up until our 2020s, we can see a steady increase in cases of HIV. And you don't have to dive deeper into the different years in between because you know that we are, in fact, on the rise when it comes to the cases of human immunodeficiency viruses. Okay? Overall, it's up to the researcher how the data is to be presented. It's up to the person presenting the data how he or she wants to present the data. But it's important to consider that each graphical representation of data, of course, would have its strengths and weaknesses. Okay? When you want to present trends, you go with a line graph. When you want to present proportions relative to a population, you go to a pie chart. If you want to present comparisons between the frequencies of different nominal variables, you go with a bar graph. And if you want to present differences in quantitative variables, you go with our histograms. So again, up to you, up to the researcher, up to the presenter on how the person is going to present their data, as long as you consider the strengths and weaknesses of the different methods or the different graphical representations of data. Okay, so with that, the presentation is at its last slide. So again, thank you for listening, and I hope you learned something new, and I hope there is something that you can apply in your day-to-day lives or in your research in the future. Okay, so goodbye and thank you.